Today's class what we are going to study is something about geometry. So before we are going to study this subject, geometry. So from ancient times, from the recorded history, from Greeks. So we have this subject is very essential, or it's not only which it has some it's a subject because it helps us to visualize, it helps us to measure things in some practical sense. When we measure quantities, when we measure our day-to-day activities, how we can visualize things. But in its essence, the subject of geometry is basically very much related with how we try to visualize something called space. So it is another way of, when we say of geometry, it is synonymous with this idea of space. And the question is, what is space? Space is something innately, it's an innate idea that you know that things, everything in the universe, whether it's mass, material, they exist in something called space. And that space is vacuum, or that space is free, or whatever that space is. Even matter is supposed to be, or imagine matter in a space. So what is space? So space, in a sense, it becomes an idea, it becomes a prior idea. Something you might have heard of a word called a priori. Or it's not, and other things which are embedded in space, they are posteriori. For example, you have things or quantities, you say something exists in space. Matter is in space. So we take space as an entity or as a quantity which exists prior, as if it has been existing there and always there.
I see.
So how did philosophers and mathematicians try to contextualize or visualize this quantity called the space, and synonymously called geometry? So if you go to books, if you go to literature, if you go to different mathematics texts from earlier classes, you can say that the school of Euclid, has been very much essential in how we try to visualize space in a form of how we can understand space in a given context or in a given systematic procedure. So that thing, what you might have heard, is all called Euclid's elements. Have you heard?
Yeah.
And there are
These books.
50. One, two, whatever that is. That's the part. And what is it? And even though, as a side comment, I would say the idea of being Euclid may be in Greek antiquity. People are disagreeing whether Euclid was one person or there are many persons. So there are contested histories. This person called C.K. Roger, he has an interesting There's an interesting observation about historical figure called Euclid, whether he was an African, whether he was a Greek, whatever that is. Whatever that may be, whoever was Euclid, he was one person or many persons. But the thing is that the elements of Euclid have been for 2500 years before, almost 2500 from Greeks, whatever their histories. These elements have been how Euclid construed space. It has been very much influential or dominant in how people appreciated or understood space in that sense. right through medieval times, even early times. Entire through study of potential physics, whole of Newtonian physics, Newtonian physics has been what I should say the basic frame or a basic vessel container by which we try to study space using Euclidean geometry. So for maybe 2,000-3,000 years, the subject was the idea of space had been canonical or it was considered standard. So this is what is space. Before, whether space was Euclidean or not. So the thing is that Euclid constructed space to be thought like this. Whether space was that or not, that's a question. But the question that so much was success of Euclidean geometry for 2,000-3,000 years that people said that space is Euclidean. Got my point?
Yeah,
very good. So that's the point, essential point. And before people could, this is another part of story. When people went from Euclidean geometry to non-Euclidean geometry, or Riemannian geometry, or many geometries, or that geometry, this Euclidean geometry is one geometry. So space can be thought
by many
ways.
Oh.
And Euclidean geometry, so this realization has been very late after the discovery of non-Euclidean geometry or late 15th century. So it has course on this Euclidean geometry. We can have there are some assumptions of might have heard in the earlier classes. There is something called actions. And there is something called
postulates.
Sure. Or there is something called
Colder.
So these are nodes. What are actions?
Loosely, they are said that self-evident truth, is it?
Yeah.
Self-evident truth.
So this self-evident truth is a very loaded term. What do you mean by self-evident truth?
Yes.
So it's a very loaded term. So loaded means what is very evident. Sometimes what is very common sense it is not. It is common sense can sometimes delude. Common things. So what is also not common, it's not necessarily. It is what's also self-evident. On a deeper analysis, it might not be that self-evident. So maybe these people talk in terms of self-evident truths, but the proper way of defining actions are there are certain statements which are true, but which we cannot prove. Statements.
How do we know then they are true?
That's the point. So this is another debate. Actions may be they are primitive statements. Which are true, but which we cannot, or true, but we cannot.
True.
What do you? So you assume something when you talk of space is prior. So as if these are sort of those Platonic elements. So there are some truths, they are eternal, which are existing. So Euclid and the school of that school, they thought that we could somehow discover them, or you can discover them, and you can catch them. And that they represented that elementarity of primitiveness. So from primitive statements, from these, or people then also talk in terms of they are they can be. Because this is for another debate, whether geometry is empirical or whether geometry is not empirical. If geometry is empirical, then this statement can have some validity. If geometry is not empirical, geometrical truths are eternal truths. So if you digress into a bit of philosophy and Platonic things, then this statement may not, this characterization is not this true. So, in simplest sense, you can say that grammatical statements are they are true statements which you cannot prove, or they are primitive statements. They are primitive statements, and if you assume them they are true, leave away what are the motivations that how people arrive at them.
I see.
Whether they arrived from empirically, for example, parallelized development, or they have to infinity, they have not gone to infinity, they then extrapolated. Up to whichever way you can, they will never quit. So whether the motivations have been empirical or not. So there is a confusion. So, but if we assume that the validity of certain primitive statements, which are called axioms, and by certain rules of reasoning, by certain rules of reasoning, which we impose upon them, we arrive at certain other statements, which we call sure or whatever.
I see.
So we can start from action. So they will be primitive statements. I will not use the word self-evident. Maybe they are primitive statements which are true,
Cannot be proved.
which we cannot prove. But if we impose certain rules of formal reasoning on them, we impose certain rules of formal reasoning on them, so we can arrive at other statements. That's which are called theorems. And from theorems we can also have corollaries. And the only thing which you might have studied in your textbooks is that imposing those rules means they should be consistent. Or rather, they should be self-consistent. So what do you mean self-consistent means? If you impose, for example, this rule that parallelize never meet, from that you can, if you have a line which is going to cut them, so from that you can say that corresponding angles are equal, or whatever alternate. But if you have those primitive statements arise, so you can go from one statement to another statement, but at the end you should come to where you started, or from where you started you should come where you end.
It should not contradict
It should
each
not
other.
contradict. Starting from a given set of actions, you can do from this deductive theoretical reasons. There is something also called deductive theoretical reasoning, which you in your earlier class called steps. I'm getting what you call steps. You go from step A to
Step 2.
What do you mean step A to step B? This is a theoretical reasoning.
Deduction.
From certain
Primitive
actions. So these are called, so this is how to appreciate. So that the statement they should be.
Self-conscious.
So if you have certain axiomatic systems, structures or systems, you can go from this to this, from this to this, so this to this, and this to this. So this means you should always have something. You can come from this to this. Whichever way you come, you should read to where you started. That is known as rigidity of this.
Rigidity.
So that way you move the mathematical structures. That's true in general mathematical structures. But here we are going to concentrate on Euclidean geometry or Euclidean systems of whatever that is, the systems, the geometrical systems. So before we are going to continue with this, so what are, for example, in the context of geometry, how there are from we are going to the next series of classes studying properly. So how there is an essential ingredient of space that when in Euclidean system, that space is made of points. Space is made of.
It's a basic axiom, is it?
Before we are going to see how we construct states. And what is the point?
Dimension, yes, yes.
So it is length, breadth, plus it's neither having length, neither having breadth, neither having. So he thought that it's too abstract.
Okay, but space.
It's the smallest. So you cannot even imagine it. It's not.
Is it the axiom of the Euclidean system?
So like action means from this first how we construct a space in the Euclidean system.
Sure.
So essential point is that the ingredients of space are points, and space is made of entire space is
Made up of points.
And now how from this we will start. How we define line segment. 2 points make a line.
Yeah.
Huh?
Mm.
And 3 points. So what he said, breadth plus length is called. Breadth plus length is called line.
Line. Say.
Breadth plus length is called. And 3 points. 3 points make it. 3 points make it.
Line.
3 points make it.
Why not 2 points?
Plane. 2 points make a, 2 points make a line in Euclidean construction. So what I want to emphasize, this is a construction. If you assume things that way, things fall.
There must be some reasons, isn't it? Why they said, as you said, logical reasoning.
So if you construct space like that, so it helps us understand a lot of things.
Okay.
So if you assume something, so when you assume something,
So it's assumption.
why are you assuming something? It might have different motivation. You leave it. Why you assume? Why Euclid's postulates are like that. But if you assume something, you can construct or you can imagine space can be thought that way. And so much has been space, so much successful in those constructions have been, we thought that space is Euclidean.
Yeah.
So you can always have the thing that we can 2 points with the plane or 3 points. You can have that whatever construction you want.
I see.
So we are talking of Euclidean construction or Euclidean constructed space. And in this construction space, you can only draw one parallel lines from a given point. Okay? From a given point, you can draw one parallel line.
I see.
From a given line, you can only draw one parallel line.
From a?
Given point.
Line segment.
I see.
You can only draw one parallel line. Although this action is later shown that from a given line segment, you can draw. But in Euclidean construction, you can only draw.
I think we can draw infinite.
So you assume it. These are some assumptions we are going to take one by one.
Is it that translating only this parallel line is like we have infinite lines?
No.
It's translating the same line over space.
Exactly. You can say that parallel lines never meet.
Yes, sir.
But you can also assume that parallel lines can meet at infinity.
Yeah.
This is another statement. But in Euclidean construction,
That's right.
parallel lines never meet. So we are going to say what is how Euclid tried to appreciate space and what are the basic assumptions and the deductions thereof, theoretical deduction therefore. And this whole scheme is called
Euclidean geometry.
It's called
Euclidean geometry.
Euclidean geometry. And then once we have Euclidean geometry in the proper sense, then we can go from Euclidean to analytic algebras. Not Euclidean one for those geometries are. Stop.
Sure. Great. Thank you so much.
Thanks.
Great.
हो गया
Okay, just later.